So we're on 9.8 to 9.11. First example, derive a general expression for the initial velocity of a ballistic pendulum as a function of height. So first of all, a ballistic pendulum, what is that? Typically, it's a block of something that's hanging, so that's the pendulum part. The ballistic part is that we have a bullet or a rock or a ball or something that hits this block and then sends it swinging. That's a ballistic pendulum. And so in this case, we want to know the initial velocity of this object, whatever this object is. We want to find what this is as a function of the height that it reaches over here, right? And so we've got two things. We've got little m and big M here. This is initial condition. The final is that this smaller thing has embedded itself into the bigger thing, and it has reached, they together have reached some height h. The mass of this thing now is m plus m, little m plus big M. That's what we've got. Okay, and so what do we have here? It's two things. We've got a conservation of momentum problem, and we have a conservation of energy problem. Conservation of momentum with the collision. Now it has some initial velocity, and conservation of energy reaching this height, right? How much kinetic energy does it have being transferred to gravitational potential energy with that height? So we've got mvi, so we're going to call this vi, equals m plus big M vf. All right, that's what we'll call that. And then we'll go over here and write our conservation of energy equation. 1/2 little m plus big M vf squared equals 2 little m plus big M gh. Not 2. I don't know why I wrote that. Little m plus big M gh. Right. So now we want to solve for this. The m's cancel out, and so vf is equal to the square root of 2gh. Right. So this now we can plug into here, and so we have m vi equals m plus big M times the square root of 2gh. So this looks good. We want this as a function of this. So now all we have to do is divide by little m. So vi is m plus big M times the square root of gh over little m. So now we have the initial velocity as a function of the height. So we know we have some ballistic pendulum, we know the masses, and we know how high it gets at the end. From that now, we can calculate what the initial velocity is. Okay, so then we have this thing about a series of collisions, a steady stream of particles, and all these particles have the same momentum, right, mv, colliding with a target in a fixed place. You can see the next example, something like this would be like a machine gun, right? A lot of bullets happening one after another, hitting some object. And so what we can do here is think of it this way. The average force vector, right, is going to be negative, so the negative of the change in momentum, n times delta p, because delta p would be the change in momentum for each individual particle, right? So we're multiplying that by the number of particles and then dividing by delta t. All right. Or we can say that this is negative n times m times delta v over delta t. But the number of masses hitting, n times the number of masses is kind of like the change in mass times the change in velocity over the change in time. So all different ways of expressing the same thing there, right? And so we have an example with this. Superman experiences a spray of 0.1 kilogram bullets striking his body at 1,000 bullets per minute. So that would be the n. Or 1,000 bullets per minute. So we need to find how many that is per second. At an initial velocity of 500 meters per second. So calculate the force on Superman if the bullet stops, and then if they ricochet off of Superman. All right. So I'm going to set it up this way. Or rather, I think this would be better. And m delta v. So I've got n over delta t because that is, I know I've got 1,000 bullets per 60 seconds. Right. The mass of each one is 0.1 kilograms. And the change in velocity in this case is negative 500 meters per second. Right. So this is going to be 833 newtons. That's it. In the second case, where they ricochet, the only difference here is that now, instead of them stopping, going from 500 to 0, they're going from 500 to 300, but in the opposite direction. So the total change in velocity, delta v, is 800 instead. And so this is all set up the same way, but for part B now, it's going to be negative 1,000 over 60 times 0.1 kilogram times negative 800 meters per second. And that result is going to be 1,333 newtons. Okay. Now, the next thing is these general equations for one-dimensional elastic collisions. In the last lecture, we had this problem where we knew the initial velocities of two objects, there was an elastic collision, and then we didn't know either of the final velocities. And we had to use both momentum and energy to solve that, because we needed two different equations that had velocity in it, two equations, two unknowns, and we had to do all this solving. It was a mess. Here is a derivation for a formula that'll help you out in any of these situations. If you know that there is an elastic collision and you know the initial velocities and you can find both of the final velocities using this formula. Okay, and you can follow it, go step by step through the whole thing using conservation of momentum, conservation of kinetic energy. It's basically doing what we did before, but with all the variables. There's one key thing in here, right? In the second page, there is this equation, V1I plus V1F equals V2F plus V2I. Right. This is one really nice, simple equation that you can use sometimes. All right, so I would say this is one that you want to memorize. Also notice here what this is. It's V1I minus V2I equals V2F minus V1F. So the difference of the velocities have the same magnitude. So thinking about it in this way is helpful also if you want to do that. So very, very helpful little equation. And then the resulting equation at the end also, that's the one you can actually solve it and it'll give you V1F when you apply it that way. Okay. So some other general equations for elastic collisions. V1F to find V2F, that's that same equation that we derived from before. So now we want to look at some special cases. What if M1 is equal to M2? So this is like the case of a billiard ball, right? Where they hit, in this case they exchange velocities. So you could say this, that V1F equals V2I and V2F equals V1I. The exchange velocities. B. What if V2I equals 0? So initially, the second object is not moving. Then in that case, one of the terms disappears. So you can see that V1F is M1, M2 over M1 plus M2 V1I, and V2F is 2M1 over M2 plus M1 V1I. C. What if they are equal in mass, though? Well, if they're equal in mass, and one of them starts off with velocity 0, V2 starts off with velocity 0, if they're equal in mass, see what happens here. oh, sorry, this should be a minus on the top. M1 minus M2. Okay, so now it makes more sense. This ends up being 0. So V1F equals 0, and V2F, if it's the same mass and you have 2m and 2m also on the bottom here, and so this is 1, so V2F equals just V1I. So again, they just they switch velocities just like here, except that in this case, V1I or V2I was 0. Right. D, what if M1 is much, much, much bigger than M2 and V2I is 0? So imagine this, we've got some gigantic object rolling along and hitting some really tiny object, like let's say it's really big, like a really heavy bowling ball hitting a ping pong ball. What's going to happen in that case? Well, what's going to happen is this thing is so big compared to this that this one, the velocity is hardly going to change. So V1F is equal to V1I. Right. This one, the velocity is really not going to change. But for the smaller object, if M2 is really tiny compared to M1, look at V2F. You've got 2 times M1 over M2 really doesn't matter because it's so small. So it's like 2M1 over M1. This is saying 2 times V1I. So in that case then, V2F is going to be like 2 times the initial velocity of the big object, 2 V1I. It's so big, this one hardly moves at all, and then this one bounces off at twice the velocity of this. Last one, what if, oh sorry, that was E, actually. So this is situation E. Apologize for that. And then what about situation F? Let me go up here. Sorry, we need to go back to situation D. So if you've got a really tiny object bouncing into some really big object, in that case, this thing, if it's so big, it's not going to change. It's not going to move. It's not going to start moving. This is just going to bounce right back off. Right? An obvious example of this is dropping a bouncy ball. And the bouncy ball, you drop it. The bouncy ball, the mass is so small compared to that of the Earth that the Earth's velocity doesn't change at all, as far as we can notice. But the bouncy ball just bounces back up, but in the opposite direction with the same speed, right? Assuming perfectly elastic collision. And so as a result, V1F is equal to the negative of V1I. And V2F is still 0 because it was initially 0. Right. And we do have situation F. This is an addition, in addition to what you have here. Right. Another one to add. This question is, when V2 is 0, V2I is 0, what percentage of energy is transferred from M1 to M2? So V2I equals 0. What percentage of energy is transferred from M1 to M2? All right, so really what we're looking at here is, K1I is K1F plus K2F. All right, it's totally elastic. V2I is 0, so there's no elastic potential, or there's no kinetic energy for the second object in the beginning. Right, and what we're asking here is, what is K2F to K1I? So what percentage, what ratio of this is now in this? So the ratio of K2F to K1I. All right, so let's take a look. So K2F is going to look like this. 1/2 M2, and then this final velocity, we can plug in what we had before. M1 over M1 plus M2 times, V1I squared over 1/2 M1 V1I squared. So some things cancel out. This cancels out with this. One of these guys is going to cancel out with one of these guys, and this is going to cancel out with this. And so I'm going to be left here with 4 M2 M1. Right, one of these M1s from here cancels out with this one, over M1 plus M2 squared. So this is the percentage of energy that's transferred to the second object, if it's a perfectly elastic collision. If M1 is equal to M2, then what we have, let's see, if M1 equals M2, so then this is 4M squared over, this is 2M, but it's squared, right? So 4M squared equal 1. That means 100% of the energy is transferred. And that's what we said before. That's the billiard ball example where they're the same mass. One of them is at rest, the other one's moving, and then they exchange velocities. So the second one is moving afterwards and the first one stops. 100% of the kinetic energy is released to that second one. So part F, question F is what percentage? It's this. And then I guess we could say, we keep going in the alphabet. The next one would be if they're equal to each other, then 100% of the energy is transferred to the next one. Right? And now this example, glancing blows. Okay, glancing elastic collision of identical masses. This is important. Every time there's a glancing blow, every time there's a glancing collision, right? So it results in 2 dimensions, things going off at angles. The angle between the final momentum vectors is 90 degrees. So let me illustrate this in this problem. We've got a gas molecule, 300 meters per second, collides elastically with another molecule of identical mass. That's nice. And after the collision, the first molecule moves off at an angle of negative 30 degrees from its initial direction. Find the speed of each molecule after the collision and the direction of the target molecule. So here's what we have. Molecule 1 is moving this way at 300 meters per second, and here's molecule 2. They're the same mass, so I'm not drawing this to scale. And what we have here, once they collide, M1 is now moving this way, and this is 30 degrees. That means that this, M2, this has to be 60 degrees, because the angle between these, where they're going off, is always 90 degrees. Okay, always. That's going to be key later on. Okay, you're going to see that. Again, it's going to come up. Glancing blows always 90 degrees. I'm saying that because I've said it before and then people forget later on. Don't forget, glancing blows, elastic collisions, 90 degrees. That's the angle between these resulting momentum vectors. Okay, velocity vectors. Okay, so these are actually really nice and easy to solve then too. One of the temptations here is to break these up into components. Find, oh, what's the horizontal component? What are the vertical components? The vertical components have to be the same, right? What do the vertical components have to add up to? 0, because what is the initial momentum, pi, in the j direction is 0, right? So we would say, oh, the vertical component has to be the same as this one, but then the 2 horizontal components have to add up to 300 kilogram meters per second, whatever times the mass, so we can calculate that. But here's the thing. We've got this momentum. These 2 momenta have to add up to this one, even as vectors. And so I'm going to call this P1I equals P1F plus P2F. And we can use vector arithmetic then. We look, oh, we can draw this out as a triangle, right? Here, this one is here. This is the m times 300 meters per second. That's got to be equal to this m1 v1f plus m2 v2f. And we can write this out even more, right? M V1I equals M V1F plus M V2F. Watch, the m's cancel out. And so I know these have to be related to each other by the Pythagorean theorem, but I also know that this is 30 degrees. So obviously not drawn to scale here. This should be like the other way. This. Wow. So you can see why I'm not an artist. This is not going well. This is 60 degrees here. So then if this is 300, that means this has to be 150, right? And this is 150 root 3. Sorry. Okay. And so the final velocities are V1F is 150 root 3 meters per second, and V2F is 150 meters per second. Right. Again, nice thing about vectors, if you've got 90-degree angles and you've got some vector arithmetic where the vectors add up in this way, then you can use right triangles. Oftentimes it's going to be a Pythagorean triple or one of your unit circle triangles, and that makes it nice and easy.